Welcome back to Calculus 1. This is part 2 of our lecture on the derivatives of polynomials and exponential functions. We're going to pick up exactly where we left off in part 1, getting to now part 3 of this lecture, derivatives of polynomials. We're going to pull some basic differentiation rules all together for this. Okay, so we mentioned at the very beginning of the first part of this lecture that trying to apply the limit definition to find the derivative of this function, f of x here is this degree 5 polynomial, it'd be brutal to use a limit definition. You might finish like next week if you were to use a limit definition. Well, we're going to slowly build up some more rules that will allow us to effortlessly differentiate this, find the derivative in a matter of seconds. Now, how are we going to do that? First, we left off with differentiating powers of x with something called the power rule. Now, what is a polynomial built out of? Powers of x. So what we're going to try to do is use the power rule here. Unfortunately, this function is not a single power of x. There's some constants, the coefficients of the polynomial that are multiplying powers of x here. And then we're adding several powers together, or subtracting, a sum or difference. So what we're going to need in addition to the power rule, which we stated in the previous part of this lecture, are some other rules. And the first here, it is a differentiation rule, but we usually don't refer to it by name. It's a rule for when we have a function that we know a derivative of already, multiplied by a constant. Typical in calculus and mathematics to write a constant as, for instance, c here. So what this constant multiple rule allows us to do is instead of differentiating a constant multiple, c times a function, we can just differentiate the function and then multiply that derivative by c, the constant. All right, that'll be one of the new rules we combine with the power rule to eventually differentiate a polynomial. Since we're adding several powers within a polynomial, we need something here called the sum and difference rule. And what this allows us to do is take a sum. So here we have two functions being added or subtracted. And then instead of differentiating the sum, we can differentiate each part and then sum, add or subtract those individual functions' derivatives together. Now, these might look familiar. Keep in mind a question we posed a while ago: what is a derivative? And we had three answers: slope of a tangent line, an instantaneous rate of change, or a limit. Now I want you to think from the third response, think of a derivative as a limit. Well, these pretty much look like limit laws. We mentioned at the time when we were introducing the limit laws, we didn't really have any use for the limit laws at the time, but they are the foundation for now. The limit laws are the reason why these new differentiation rules, the constant multiple rule and sum difference rule, are true. They look almost identical, and that is because derivatives are limits. Recall the limit definition of the derivative. Now, this is all just the technical side of things for where these laws come from, but we're going to see within kind of a little bit, very shortly, how we combine the power rule, the constant multiple rule, and the sum difference rule all together to easily answer what this derivative is for the function at the top of the page still. All right, so that's going to be basically how we proceed. We already have the power rule. We just now have to combine the power rule with the constant multiple rule here and the sum and difference rule. Putting all that together, we can now easily differentiate polynomials. So let's go ahead and get to that with a bunch of examples. Now, this is going to be 4 parts. Typically in class, I'd go through at least 1 or 2 parts together to get students comfortable and build up their confidence. And then I would turn over, for instance, maybe parts B and beyond to my students to try. As typical in a math course, we go through an easy example together to build your confidence, and then we completely crush your confidence with the following examples. being a little dramatic here, but the following examples, B and beyond, do get a little trickier. So let's go through part A together, and then I'll let you pause to give yourself an attempt at part B. I will say before we start part A, the work we're going to put on the screen here is not typically all the work that I would like you to do a little bit later in the course from now. Now, this first example, part A, we're going to meticulously apply each differentiation rule, the power rule, constant multiple rule, and the sum or difference rule within this first example. After part A, we're probably not going to apply those rules one by one, but we'll just start incorporating them as part of our skill set. All right, so let's go through part A together. All right, I want you to notice this function y equals here, a polynomial. It's built out of powers of x being multiplied by constants, and then we're adding or subtracting, forming a sum or difference of terms. All right, so what we can do first here to find the derivative, which we're writing in Leibniz notation, we can differentiate each part. We have here a sum or difference of 4 terms. The sum difference rule allows us to add or subtract the derivatives individually of those 4 terms. All right, notice now for the terms, the functions in brackets, we have some constant multiples. So from here, we can apply the constant multiple rule to bring the constants 2, 4, and 3 in front of the derivative. And what's left in the brackets now are simple functions that we can differentiate using the power rule. Notice at the very end there, the derivative with respect to x of 7, we're going to interpret 7 as a constant function. And you might recall the derivative of a constant, the derivative of any number equals 0. Again, this work here is not as we're going to go through it as we start getting into typical calculus problems, but it is how we apply those basic differentiation rules. Here, once we have broken it down, we've now taken a complicated problem and broken it or split it into simpler problems. Here, the simpler problems just rely on using the power rule. All right, so if we calculate those individual derivatives with the power rule, the derivative of x cubed, 3x squared. Derivative of x squared would be 2x. The derivative of just x is 1. And then derivative of 7, which is a constant, equals 0. And we just put all that together and then do some basic math, and we get a nice simplified derivative here, 6x squared minus 8x plus 3. Now, before we go on to part B, which I'll pause and give you an attempt at, typically what we're going to show for work is incorporating kind of all those first 3 lines of calculus there within our work. And some of you might be comfortable doing that already, going directly from the function up there, y equals 2x cubed minus 4x squared plus 3x plus 7, and kind of incorporating all 3 of those rules together: the power rule, constant multiple rule, and sum and difference rule. And that basically skips 3 lines of algebra there, going very quickly to the answer at the end. All right, so let's advance. I'd like you to pause and give yourself an attempt at part B here. We'll check in a few minutes. All right, hopefully you were successful with this. This is very similar to part A. The only difference is now that we're going through this, I'm going to assume that you feel comfortable with part A. If not, go back, rewind, pause, make sure you thoroughly understand part A for jumping into here. When we go through this work in a few seconds, we're not going to apply as writing by hand, applying each individual rule, the power rule, constant multiple rule or sum difference rule. It's not too hard for most students to incorporate all those together. So this function here, the factor of 4, 3, -2, and 5, they just stay as constant multiples. The only thing we need to focus on here to find the derivative, f prime of x, is just differentiating the powers of x, x to the 5th, x to the 4th, x squared, x, and 1. We're going to incorporate the constant multiple rule all together and already basically use the sum and difference rule to differentiate each term individually. All right, and I think it wouldn't be too bad to jump straight from the function to this derivative. Typically after a small number of examples, most calculus students are quite comfortable incorporating all three of those rules together to go from the given function to its derivative here. Again, 4, 3, -2, and 5 are constant multiples, and they just multiply the individual simpler functions, the powers of x's, and their derivatives. All right, the rest of it here is just cleaning this up, just multiply out, and we get our derivative here as 20x to the 4th plus 12x cubed minus 4x plus 5. And that's typically the work that we're going to kind of show together when we go through our recorded lecture. And it's typical of, I guess I would say, what I'd be looking for in the work for a well-prepared calculus student. Don't apply individually the sum and difference rule, then the constant multiple rule, and then the power rule. It's not too hard to combine all three of those together as we're showing here. All right, when you're ready, let's move on to part C. And this one is similar, but it looks a little different. Now, if you haven't already attempted this, pause and give yourself an attempt at part C here. This one is a little different. You might have to rewrite it. We'll check in about a minute. All right, if you're ready, let's go through this. Now, this is not a complicated problem, but I want to make sure you see the connection. Hopefully, parts A and B were pretty simple. Now, part C is a little different. Ignore the different variables. We've been using x, but here the variable is t. That's not the thing I want you to notice here. What I would like you to make a connection with is we have a function written in factored form. If you multiply this out or FOIL or expand it, you can then make that function look like what we have in parts A and B, a function written in expanded form for a polynomial. Now, again, this is one of our kind of central problem-solving techniques in calculus. Rewrite your function, and you can basically have a more easy time to achieve your goal. Typically, in calculus, you're interested within the first few courses or lectures, finding the derivative of a function. So here, the tip, which is really important. Notice it's not in one, but 2 boxes, which means it's like really important. We're just going to multiply, FOIL, or expand that. And then that looks like a polynomial, except now we're using t as the variable rather than x. Basically, by multiplying this out, it easily turns into a problem that's simpler than part B. So from here, if you didn't notice that, re-pause and see if you can complete the problem. All right, so let's wrap this one up. Just as we did in part B, we can apply the constant multiple rule, sum and difference rule, and the power rule all together. The power rule does apply even though our variable is t here. Make sure you are comfortable switching between different independent variables. X is very common, but so is t. Once we get access to differentiation rules, which we're learning about now, we can start coming back to some of those interpretations as derivatives, as rates of change. And then we can start getting into physics types problems related to position, velocity, and acceleration. A little hard to do that with the limit definition of the derivative, considerably easier to answer those types of questions with differentiation rules. Okay, so if we differentiate the expanded version here, 4t squared minus 12t plus 9, it's pretty effortless to calculate the derivative with our 3 basic rules. Differentiating term by term, the derivative of t squared is 2t, the derivative of t, like x, is 1, and then the derivative of 9, a constant, would be 0. And we just clean that up and we get our derivative here as 8t minus 12. Now, before we move on to part D, let's just start, incorporating some physical interpretations to prepare us for kind of a lecture coming up, derivatives as rates of change, in which we'll explore that in detail. Let's suppose here the function given in part C, s of t, let's suppose we interpret that as the position of a function or an object at time t. All right, so s of t is the position function. At each value for t, you get the position of the object. What might then the derivative represent? Well, the derivative of position, we would interpret that as the instantaneous rate of change of position, which is what we call velocity. So if s of t denotes the position of an object, s prime of t, that represents the object's velocity. And now you can see with differentiation rules, those questions are considerably easier to answer. So if s of t represents the position, we're called the position function. S prime is then the velocity, or velocity function. All right, when you're ready, let's take a look at part D. This one is the most complicated of all. And it's like we mentioned earlier in a few spots, it's not complicated for the calculus reasons. It's complicated for algebraic reasons. Now, I'm putting that same tip that we used in part C back here. It's the key to this question. Rewrite this, and that will really test to see how good your algebra skills are. I'm going to be vague about how to rewrite it, but rewrite it, and then it should become very easy to differentiate that. Give yourself realistically here at least several minutes, 3 to 4 minutes. We'll check in after that. All right, are you ready? Again, here, this problem, it's really an algebra problem in disguise. Now, I will say, typical in a calculus course, there might be several ways to answer this. We haven't yet learned about something called the quotient rule. When we do get to the quotient rule, which is pretty much the next lecture, we'll be able to approach this problem in a different way than we are right now. The way we're going to approach this is we can rewrite this as basically a sum of a bunch of powers of x. The things to notice here is square root of x. We can rewrite that as x to the 1/2 power. And then since we have a division by just a single factor, x squared, we can kind of split that fraction, the 3 terms in the numerator, we can divide each of them individually by x squared using some basic rules of fractions. Now, if that was enough of a hint for the light bulb to go off, maybe re-pause and give yourself an attempt, and then we'll go through it. So when you're ready, maybe that was enough of a light bulb moment of how to rewrite it. Give yourself an attempt. If not, just proceed. I'll pause for a few seconds. All right, so again, the tip here is to rewrite it. first thing we can do is replace square root of x with x raised to a power. Square root of x, we can rewrite that as x to the 1/2 power. All right, next, we're going to notice we have several terms in the numerator. I can divide x squared, the denominator, into each of them. All right, so we have the basic fraction rule over on the right there in red. So we can write this as a sum of 3 separate fractions. The denominators, or what we're dividing by, are all x squared. All right, and then from here, we are dividing powers of x. And you might recall when you divide powers of x, you do what with the exponents? Subtract. So we just use this basic exponent rule from algebra. X to the m divided by x to the n. We just subtract and get x to the m minus n. Now it gets a little tricky here for that last fraction. As warned, the presence of fractions kind of increases the difficulty for a lot of students. Just make sure you're comfortable. We are subtracting the exponents, but what we're subtracting now is 1/2 minus 2. So just use a common denominator. 1/2 minus 2. Think of 2 as 4 over 2. That'll come out to -3/2. Now, this is no calculus yet. We're not applying the power rule for derivatives. We're just applying some exponent or power rules for powers of x. All algebra. All right, now let's pause just to see what we've done. We started with y as a fraction. We were able to rewrite that kind of at the bottom here, the very last line. We can rewrite that function equivalently as x plus x to the -1st power plus x to the -3/2 power. Now this is technically not a polynomial. Polynomials only have positive integer exponents, but it's very similar. It's an expression that's a sum of powers of x. One of the powers is negative, actually 2, and one of the powers is a fraction. But the power rule differentiates them nonetheless. So here, most of the work is rewriting this function. It was all just a bunch of algebra, and now we can just basically apply the power rule. Right, so there's the rewritten function, just to have the work a little more clean, above and below the derivative. Here, we're just going to apply the sum rule and the power rule. X is going to differentiate to 1. We differentiate x raised to the -1, bring the exponent down. That gives you the factor of -1. The new power of x would be 1 less, x to the -2. And then we also apply the power rule to differentiate x to the -3/2. Again, just be careful with fractions. The power rule for derivatives says that we subtract 1 from the function's power of x. So we have -3/2 minus 1. That comes out to -5/2. And that's it. Again, notice the presence of fractions likely made the problem seem more difficult for you, but really take time to kind of see that it's really the same. It just only seems more complicated, since fractions for most students, I realize, are kind of a difficult thing to deal with. Okay, so from here we can just rewrite this. And it's fine to leave this answer here in this form. Just realize you could rewrite some of these negative exponents as reciprocals, 1 over a power of x. You could rewrite the -5/2 power as some sort of radical, but you don't have to do that. So leaving your answer here for y prime in this form is completely fine. All right, and that concludes the 4 parts of this example. Now I want to take a look at an example where the calculus is actually pretty simple, but there's some, I guess, conceptual difficulties that we're going to start to incorporate in some of the questions. So let's move on to a follow-up example. The actual calculations are very similar, but there's some new concepts thrown in. Okay, so definitely pause and give yourself an attempt at this. We haven't talked about finding the equation of a tangent line for a little bit. So we're going to come back to that here. We have our function here given as x cubed minus 12x plus 4. And then we're asked two parts. For that function, find the equation of the tangent line. So find the equation of the line tangent to the graph of that function at x equals 1. And then part B, a kind of new question that we'll keep coming back to throughout the rest of our course, is we're going to find points on the graph of that function where the tangent line is horizontal. Now, what I would not like you to do for part B is to graph that function and then find those points where the tangent line is horizontal from the graph. Keep in mind, one of the goals we are working towards in our course is eventually being able to sketch a curve or sketch the graph of a function. The ideas we're developing now will assist us with that. So see if you can answer part B algebraically. Part B is a little challenging. Part A just really requires you to recall the equation of a tangent line. Both parts A and B require you to have the derivative. So for most questions at this point in our course and beyond, you're calculating a derivative at some point. So pause, give yourself several minutes to attempt part A and B. Almost everything follows from first calculating the derivative. We'll check in several minutes. All right, let's go through part A. Part A is not a tricky or difficult problem, but if you don't recall the basic formula for the equation of a tangent line, then you're likely going to get stuck. So here is the standard basic version for the equation of the tangent line at some point A. And for the problem, we're told find the equation of the line tangent to the graph at x equals 1. In this formula, we're going to use A as 1. All right, there's really only two things we need to calculate: the function or original function evaluated at 1, and then the derivative. So first, let's calculate the derivative. That should be very minimal compared to parts A and B of the last example. Those had more terms. This is only 3 terms. So we apply a combination of power rule, sum and difference rule, and then the derivative of a constant, as well as the constant multiple rule. All right, so just make sure you're comfortable with that. X cubed differentiates to 3x squared. 12x differentiates to 12. Keep in mind the derivative of x is 1. That comes from the power rule. And then the derivative of 4 is a constant. It's not multiplying anything. So 4, we think of it as a constant rather than a constant multiple. Every constant or number differentiates to 0. All right, so the derivative now with our differentiation rules, that goes really quick. And now we can quickly get to the conceptual problems. For part A, it's just knowing the equation of a tangent line. So we need two things. We need f of 1. That's your y coordinate. So we plug 1 into the original function, f. So you should get -7. All right, and then for the slope, and recall, we interpret a derivative as the slope of a tangent line. We plug 1 into the derivative, f prime here, and we get that comes out to -9. And at this point, we're basically done. We have our y value, and then our slope, and it's just plugging into the equation of the tangent line above. Just be careful on the left side. The formula is written as y minus y1, or y minus f of 1. And here, f of 1, that function or y value is negative. So just be careful. You have minus and negative, which is really positive. There's a sign cancellation. And we get our equation there. Notice that everything followed once we had the derivative. Now, a nice way to cheat in the course, and it's not really cheating, but It's a way to quickly answer the question or get some partial credit. If you have no idea what to do for a question, calculate a derivative. And that's really the key to part A here and the key to part B. All right, let's go through part B. It's the same function, but now with the same derivative. So we already calculated that from the previous part. Now we just have to kind of address a new conceptual question. What would it mean for a tangent line to be horizontal? All right, let's start to layer some ideas together. How would you first find the slope of a tangent line? Well, slope of a tangent line, that comes from a derivative. That's one idea. What's the slope of a horizontal line? 0. So we have a horizontal line has slope 0. Now we're going to combine those two ideas together. The slope comes from the derivative, but since the line, tangent line, is to be horizontal, we want its slope to be 0. So what we get here, combining those two ideas, is this algebraic idea to find where the tangent line is horizontal. We solve this equation. We solve where the derivative equals 0. And this is our first time encountering this, but solving this equation, f prime of x equals 0, is a kind of a central topic in a lot of different questions in calculus, I'll say. So we're going to keep coming back to this, set the derivative equal to 0. Here, we're doing so because we want to find where the tangent line equals 0. And that 0 is there. 0 is the slope of a horizontal line. All right, now this is going to be a good example to show you that very quickly we get through the calculus in a question, and then we're just left with an algebra problem. So our derivative up there, f prime of x equals 3x squared minus 12, we now set that equal to 0. And at this point, we're done with calculus, and it's just turned into an algebra problem. Pause and see if you can complete this algebra problem. Solve that equation for x. Realistically, if you're well prepared, you should be able to get through that very quickly. We'll check in about a minute. All right, now you could have solved this in one of several ways. This does factor. That's always a good way to solve a quadratic equation. So try factoring. You could have also isolated x squared, add 12, divide by 3, and then take a square root. So isolating and then using the square root property, that's another way to solve besides factoring. And then a third possibility, to solve any quadratic equation, you could use the quadratic formula. And you should be able to confirm your solutions for x here using all three methods. If you want to be well prepared for the course, work that out using all three approaches: factoring, using the isolation and then square root property idea, and then using the quadratic formula. Confirm that you get the same answers for x using all three approaches. A student that aims to be well prepared and do well in a calculus course should try that on their own. Now, just for brevity and to keep the lectures within 30 to 40 minutes, the recorded lectures, let's just go through one approach. This you can factor. So you can first factor out 3, and then the remaining term, x squared minus 4, that is a difference of squares. So you can fully factor this. Since it's factored and equal to 0, you can now set each factor to 0. And setting x plus 2 to 0 and x minus 2 equals 0, you get two simple linear equations giving you solutions x equals -2 and x equals +2. And we're pretty much done. Now, just to be technical, the question was asking to find the points. Points are listed mathematically as an ordered pair in x comma y. We only know the x coordinates. Now, we have reviewed a little earlier in the course. How do you find y coordinates? Well, given an x value, y coordinates come from the function, the original function, f, not the derivative. So to get the y coordinates, we just plug -2 and 2 into the function to get these y values, 20 and -12. All right, and that completes this example. Part B here of example 2 was kind of an important topic, so make sure you thoroughly understand that before going through the final part of this lecture, part 3.